Okay, so we're going to get started on the next section. It's my pleasure to introduce Daniele Oriti, who's going to be talking about cosmology as quantum gravity hydrodynamics and the fate of cosmological singularities.
Yeah, thank you. So, and now for something completely different. Can you hear me okay? So I'm going to discuss a view on cosmology starting from supposedly fundamental quantum gravity theory. So I will first of all outline which perspective on quantum gravity informs the view on cosmology that I'm going to present. And I will keep it general and then try to give examples of the implementation of the view, both of cosmology and of quantum gravity, in a specific formalism. I also apologize for those of you who have already heard part of what, or a good part of what I'm going to say in previous conferences or talks. So I hope that on the one hand, repetita iuvant, so you just benefit from listening again to the same thing, in case you have not fully understood them at the beginning, the first time. And I also hope that for those who understood it, that Butterfield is right, and that you feel the pleasure of hearing something you actually understand well. So, what happens to space and time in quantum gravity depends on which quantum gravity formalism, of course, and also what you mean by quantum gravity. The traditional, the standard view is that quantum gravity is a quantum theory of the gravitational field, so it's some quantized version of general relativity or some other classical modified theory. However, there are 2 points to notice. On the one hand, there are several results in classical and semi-classical gravitational physics that seem to suggest a more radical breakdown of the continuum framework and of the whole idea of effective field theory. And I just list some. None of them amounts to a proof. You can feel that something more serious is suggested by one of them and not by the others. But altogether, I would argue, give a strong case for at least suspecting that something more radical happens down there. In particular, the general suggestion would be some sort of breakdown of locality or breakdown of continuity and therefore some form of discreteness for space-time. And both aspects are cornerstones of our understanding of what we mean by space-time. So in this sense, the moment either some sort of discreteness is there or some form of non-locality, then you could say the space-time itself is emergent from non-traditionally spatio-temporal building blocks of some quantum nature. So I will call them, since we are friends for many years, I will call them colloquially as atoms of space. The second point is that quantum gravity approaches themselves, whenever they come up with more concrete proposals for what the fundamental degrees of freedom of the theory are, they seem to suggest fundamental degrees of freedom that again are not just quantized continuum geometric fields. This is true in several quantum gravity approaches. In the following, we'll focus on only one of them to give an example, a more concrete implementation. So somehow space and time disappear as we know them and they're substituted by something else. And I found no more realistic picture of what's going on, nor anything coming from experiments. So, again, let me reiterate, the general idea is that quantum gravity should rather be understood as a microscopic theory of some form of pre-geometric quantum degrees of freedom. So a quantum theory of the atoms of space. In this view, the gravitational field itself is not fundamental, it's the result of collective dynamics of something else. Space-time and geometry are emergent entities obtained from some form of coarse graining of fundamental more fundamental degrees of freedom. So in this sense, you can also say that almost by definition, quantum space is some sort of background-independent quantum many-body system. This is not per se a non-trivial statement. The moment I have quantum degrees of freedom, they are interacting, I have a quantum many-body system. The point is just to emphasize the shift in perspective. In particular, the extraction of space-time from such a system and of cosmology becomes similar to the typical problem in condensed matter theory, that is to go from some atoms to some effective macroscopic description. So it's just the shift in perspective that I'm emphasizing. So space-time is emergent, fine, but I would like to also refine a little bit the notion, pointing out several possibilities and several senses in which space and time could be emergent. What I call level 0, space-time can emerge simply because, like in any quantized gravitational theory, so in the more traditional perspective, a classical space-time has to emerge from a quantum space-time. But still, the fundamental degrees of freedom are quantum continuum geometries. This is, okay, this is a form of emergence of space and time. However, if continuum space-time and geometry are obtained from different structures, then you are asked, are they just a regularization tool, in which case there's nothing more fundamental to think about? The physics is still the fully continuum one. Or are they physical? If they're physical, then you have a different sense in which things emerge. This is what I mentioned earlier. You have to go from some fundamental atoms of space to a continuum space-time, and this will involve necessarily approximations. There will be no space-time outside a certain approximate regime. This is what I would call more properly emergence of space and time. In general, if you go from microscopic fundamental degrees of freedom to collective descriptions and approximate descriptions, this generates a variety of possible phases for your fundamental system. If different phases are possible, and again, they are physical, then you have a second level, meaning that you also have to realize that the emergence of space-time is not only approximate, but is also possible only in one of the particular phases, one or more of the particular phases of the underlying system. And this is, okay, you can call it emergent plus or be a bit more clever than I am in finding names. If the atoms of space are physical, and they can organize in different phases, then you can ask, are they, all the different phases, physical? Or again, just artifacts of the mathematics of my theory. If they're physical, then maybe the phase transitions are physical, and a whole new level of questions is raised. And the transition from a non-geometric to a geometric phase already at the continuum level for the full system will be something that you also need to characterize, and is what I call geometrogenesis. So there may be some new physics there as well. And so again, in the same lack of creativity, I call it emergence plus plus. So let me say a few more words about the implications of the different levels. So at level 0, when you just go quantum, but you keep the same type of degrees of freedom, you still have different variances in the continuum theory, so you can still argue as in the classical theory. So in a sense, there's no preferred time, no preferred space, and generic solutions of the theory would not select any preferred directions in time or space. And then you have quantum nature for all the space-time observables, but the fundamental entities are still space-time fields. Still, you have a lot of physical and conceptual issues, as you know very well. So you have to identify physical quantum states and observables, first of all. That's part of the construction of the theory. Then you have to control the classical approximation of those physical states and observables, and that's a super hard problem in any quantum field theory. And then you have to make sense at the more conceptual level of the quantum nature of space-time, the possibility of fluctuations in causality, in any geometric quantity and so on. It's already a list of very, very hard problems per se. I'm just going to point out that unfortunately it's even worse than this. One way to extract maybe an approximate notion of time and space at that level is the usual relational strategy, in which you select some internal degree of freedom to play the role of a clock or a rod, and that gives you a notion of locality and evolution. In any case, even staying at this level, I'm going to argue you need new foundations for quantum mechanics, because all of quantum mechanical interpretations I know of rely heavily on notions of space and time. So we are in big trouble already here. When you go to non-spatio-temporal entities, things are worse because you still need to control the quantum properties and dynamics of the fundamental entities. You need to have a theory, and it's a hard problem. And then you also have to identify a new level, a new type of approximation. You have to show in what approximation you have some approximate notion of continuum space-time in geometry. Maybe still quantum. So you reach level 0, you still haven't done. But of course, to be a physical theory, you need observational signatures of everything you're saying. Otherwise, it just words. At the more conceptual level, I frankly do not know.
Just one question. That step may not be necessary, right? It may
Observational signatures.
No. The passing from the atoms of space-time to some type of continuum, quantum space-time.
Sure. Somehow you can go directly to a classical space-time.
There may not be that step.
I agree. I'm just saying that conceptually there are these different steps. You may be able to take both at once if you want, or just bypass completely one set of problems and arrive directly at the classical.
Or never had even the possibility of having that.
Sure. I'm just listing the logical possibilities on the table. At the conceptual level, you are in big metaphysical troubles already at level 1, because I'm not aware of well-defined notions of identity, change, causation, and so on without space-time, that somehow implicitly do not rely on some notion of space and time. So you have to do a lot of work. If you have different phases, then you need to study them at the physical and mathematical level. That you can also decide as philosophers to leave that to physicists. But again, the same ontological and epistemological problem will acquire a whole new level of complexity. You have to deal, in particular, with degrees of freedom that, because they can equally well, depending on parameters or additional conditions, give rise to a geometric phase in which, in some further approximation, you have a space-time, but also same degrees of freedom give rise to a non-geometric phase in which no approximation gives you a nice space-time. It means that those degrees of freedom are even more deprived of spatio-temporal features than you may have suspected or hoped at level 1. The moment you consider the possible physical nature of phase transitions, well, somehow it means that you want to give some physical meaning to the motion in theory space, in the space of coupling constants, in the space of possible effective theories. And again, that's also not easy. So we'll discuss all of that later on in some examples. In one example, I'll just list again the various levels so that you can keep them in mind, and when I discuss some more concrete implementation, you try to identify all these elements in more concrete terms. Okay, so now I give you an example of a formalism. Of course, I don't give you the details about the formulas. They're totally, well, they're sort of irrelevant for most of what I'm going to say. The basic idea is usually a picture, and it's just that you start from the assumption that your fundamental degrees of freedom can be pictured to help your intuition as little building blocks, tetrahedra, or use some other polyhedron, doesn't matter. which a priori, so in general, in the most general state, are not even connected with one another, and in fact even the discrete geometry is not sharply defined. But they have the sort of degrees of freedom at the quantum level that in a classical limit, individually would give you simplicial building blocks. You can, the second point that may be relevant is simply that you can characterize the simplicial, classical, and then quantum geometry of these building blocks, the tetrahedra, in terms of purely algebraic data taken from the groups and representation theory. That's the only content of this slide. You can define fully the geometry of the tetrahedron, either using, at the classical level, either using this phase space, the cotangent bundle of the rotation group, or, with some extra conditions, the cotangent bundle of the Lorentz group. And there is a relation between the two, and you can write down all the equations relating the two descriptions. In practice, the implication of this is just that your classical and then quantum theory of a single or many tetrahedra is based on a Hilbert space that could be given just as functions on the group. That's the only point. Second point is that once you have one tetrahedron described by this type of Hilbert space, you can take a Fock space. You can, of course, now the function analytic subtleties, but let's take, instead of one, you have n copies, you have n particle state. Then you take n possibly to infinity, you have the full Fock space. And you can rewrite the whole theory in terms of creation and annihilation operators. And any observable, like the total volume you attribute to a generic state, is the sum of the contributions for the simplicial volumes of each of them, which are well-defined discrete quantities for each building block.
This would be 4 volume.
3 volume. These are tetrahedra. So tetrahedra are 3 building blocks, are 3-dimensional building blocks.
I thought you were starting from simplicial.
3-dimensional. No, that's the picture. 3-dimensional building block. And if you want to think
atoms of space,
a little bit ahead in 4D, that this is sort of boundary data for a 4-dimensional would-be space-time. These are the states, and then you have to tell me about histories or interaction processes. So you have many quantum tetrahedra, and you have what is basically a field theory description for them, because there's a second quantized picture for the many-body system. And the Fock vacuum means that there's no tetrahedron, no degree of freedom whatsoever. Single particle state, a tetrahedron, labeled by algebraic data. Many-body states, including those in which you glue together the tetrahedra. These are additional conditions of the many-body states. Then you can actually, so okay, then again, a generic state will be not spacey at all. It will have no property of space, not even at the discrete level. If you start connecting them, at least you have some notion of discrete space, but you're again far removed from any continuum space or space-time. If you write down a field theory action for that, you're specifying a model for the dynamics of such a system. Yeah.
So can you go back? Can you go back and explain how they are connected? How did
I didn't explain it because I didn't say it. But I can tell you, the rule for connecting them is if you have 2 tetrahedra, so you can take a tensor product Hilbert space of the 2 Hilbert spaces for the 2 tetrahedra. A connected state is a particular type of entangled state between the 2. Maximal entangled state, actually. So you can write down a dynamics for such a system at the classical level first. You can think of the possible interactions here. The guiding principle could be, in a class of models, is that you think of the fundamental interaction as the fundamental building block of a 4-dimensional discrete space-time. So if you have tetrahedra, the basic way in which you can glue them to form a 4-dimensional lattice is to consider them as the boundary of a force simplex. That dictates what sort of interaction you put here. In any case, this is model building. You choose an action that specifies the dynamics for your degrees of freedom. In this class of theories, the quantum level, the result of this type of choices is that when you expand the theory in Feynman diagrams, the diagrams are triangulations to one dimension higher. And the amplitude is what the theory says about the quantum interaction processes of these diagrams. The quantum probability of such diagrams. So you sum over triangulations with some amplitude.
Daniel?
Yeah.
We're used to do these kind of things in field theory, in which we say, we specify the dynamics by proposing this and interpreting as a Feynman diagram. But here we don't have space-time. We don't have a rule. And as you said, we don't even have a quantum theory. The quantum theory will have to be built.
No, so far we have a quantum theory simply in the sense that I can assign probability amplitudes.
Probability of what?
Okay, wait, I don't want to enter now the discussion about the interpretation of the corresponding quantum theory. We have a quantum theory only in the sense that we have Hilbert spaces, scalar products, transitions between the two endpoint functions, and so on. The interpretation of that, for some of them we have ideas, for others not.
But you use many words that have a heavy interpretational.
Yeah, but they also
thing,
like
like
mathematical translation.
Sure.
I agree with that.
Transitions.
I'm postponing the question. I don't want to decline answering the question sooner or later. I'm just saying that luckily there is a translation in quantum field theory formulas for all those concepts. Those mathematical translations have the exact counterpart here. The interpretation would have to be worked out almost from scratch for most of them. But it just, I have 1 hour, no,
Sorry.
2 years. Even to discuss it, let alone solve the problem. Okay, so because of just the ingredients I gave you, I'm justified in mentioning, without explaining, that the type of formalism I discussed has immediate relations to a bunch of other quantum gravity approaches. So it's not something that I or anybody else came up with out of the blue. They've been either constructed out of some of these other approaches or related and justified in various ways from other approaches. Okay, so we have a good, I can add another piece of information that we have a good understanding of the relation to discrete gravity, like Regge calculus, lattice gravity, path integrals, for this type of models, for not all of them, but most of them. But still, it would be a relation to discrete geometric structures. The continuum limit, from the point of view of this type of more abstract quantum field theories, is the problem of the renormalization group of the field theory. It's the problem of controlling a larger and larger number of interacting quantum degrees of freedom, which is a more abstract way of defining what renormalization group flow is about. And so there is a long list of works and literature on group field theory renormalization. And the basic idea is just to treat it as an ordinary field theory, again, in terms of the mathematical formulation of the flow. I can, of course, tell you more about it. The general results, only one of which I'm going to use in the following as an inspiration, is that we know of large classes of models which are perturbatively renormalizable with UV fixed points, even in a fully rigorous sense of mathematical physics. And at non-perturbative level, there are at least hints, because it's much more difficult, there are hints of phase transitions, including hints of condensed phases. This idea of a condensation is what I will bring forward from these more mathematical results to the attempt at extracting effective continuum geometric gravitational physics. Okay. I'm not going to discuss other results. Yes.
So do you see a emergence of the separation between time and space in this approach? Does it look like you're constructing a four-dimensional Euclidean theory?
No, because the signature of the effective continuum description turns out to be the result of the type of group you choose at the beginning, which at first only has interpretation of giving a local light construction inside each building block. But then it percolates, if you want, to the continuum. So if you use the Lorentz group, the SO3 one, the type of observables you have in the effective continuum will be Lorentzian, and if you start with the Euclidean group only, like spin 4, the four-dimensional rotation group, you only have Euclidean observables later on. This is the general guideline. Of course, so we know from dynamical triangulations, from all sorts of other approaches, that you have to be very careful in just assuming that because you have some structure at the discrete level, you're going to get a similar structure in the continuum. For example, the dimension could be very different, even if you start with four-dimensional building blocks. But okay, this is what we know so far. I'm not going to discuss other results, just to let you know that there are other results. Now, what is cosmology in such a quantum gravity emergent space-time scenario? Again, in a way in parallel with the distinction between quantum gravity as a quantized GR and quantum gravity as a theory of some new type of degrees of freedom from which space-time emerges, you can have two views on cosmology. One is that cosmology is just the sector of the gravitational theory that deals with homogeneous or close to homogeneous global observables. At the quantum level, you may just try to quantize that sector, and that's the idea of quantum cosmology, which has a lot of results. From the point of view in which space-time itself is the result of a coarse-graining approximation to a different type of degrees of freedom, well, comes a correspondingly different view on cosmology, in which cosmology is even more the result of a coarse-graining, because you really want to coarse-grain your description from whatever are the fundamental non-space-time degrees of freedom only to those space-time observables which are also global in nature, and possibly also in a regime which is, in a certain suitable sense, close to equilibrium. This is basically the definition of an hydrodynamic regime. At least it's the intuitive picture of an hydrodynamic regime. In this sense, you could say that in a theory of quantum gravity, within which space-time is emergent as a collective notion, cosmology has to be first of all looked at in the hydrodynamic approximation of the underlying theory. If that is true and you follow how, what the template is for extracting hydrodynamics from a quantum many-body system, then you should expect that the basic variable of the corresponding cosmological rewriting of the theory should be some sort of single body density function over the geometric data of mini-superspace. This is just following the standard reconstruction of hydrodynamics from a quantum many-body system with the appropriate translation terms. A theory that gives equations for this type of single particle, single body density, which is a function of mini-superspace data, will be some nonlinear dynamics for such density. So it's sort of a nonlinear generalization of quantum cosmology. But of course with a totally different interpretation, because you're not going to have a linear structure for solutions of the equations. So no Hilbert space for mini-superspace wave functions. And in the same spirit, what could be the interpretation of a transition from a non-geometric to a geometric phase? You can say, well, maybe there is a cosmological interpretation to that phase transition. It's exactly the regime where the usual description fails and possibly even the hydrodynamic approximation fails, that is the Big Bang. So maybe in this picture, what replaces the Big Bang in the full theory is the breakdown of the hydrodynamic approximation associated to a geometric phase transition. Okay. So this gives a possible hypothetical cosmological interpretation for the geometrogenesis process. And this is a picture. Okay, if you realize this type of idea, you're going to be facing the next step, which is if I want to really interpret this phase transition as an event in the history of the universe, I want to extract predictions, I want to somehow make sure that there are some physical signatures of this hypothesis, you will have to face the problem I mentioned earlier, which is to connect temporal evolution in the geometric phase to evolution in some quotation marks on theory space. So with the RG flow that connects different phases of the underlying theory.
So that's going to be an hypothesis?
Well,
what you just said is going to be an hypothesis?
That there is a transition is an hypothesis, that it has a geometric interpretation, that it has some physical signature is an hypothesis. What I would claim is not an hypothesis, but after you accept the previous ones, is a necessity, is that in order to be able to say that there is some physical signature, you must locate the phase transition at the would-be Big Bang in the classical theory. And so somehow you have to connect evolution in the geometric phase, where you can talk about early universe and the Big Bang at the classical level, with the evolution on theory space. Otherwise, I don't know how to in what sense I could say that the non-geometric phase is what the system ends up being on the other side of the Big Bang.
No, I agree that sounds like the only kind of thing. I agree that this is
I'm not saying it's true. That, in the sense, is an hypothesis. I'm saying that you have to face this problem as a logical consequence of the other assumptions. Or of the facts. I suppose that you do find a phase transition and that the theory says there may be some physical consequence. In order to really exploit that, you will have to answer this question. Okay, and now we will discuss how to implement one implementation we found of all these ideas in the quantum gravity formalism that I introduced earlier. Okay, so in case you're already tired and you want to nap for 10 minutes now, I first flash the main ideas. The rest would be a sort of implementation of this. So, first hypothesis, we assume or we focus on a condensate phase for extracting the relevant continuum physics. As I said, this is supported by some results in group field theory normalization, but none of them is fully conclusive, so it remains an hypothesis. We focus on that. We have to choose on what sort of states, what sort of approximations to look at in the complicated formalism, and we focus on condensate states. Then we look for the hydrodynamic approximation of the full quantum dynamics for condensate states in the full theory. So it's a further hypothesis that you have to look at the hydrodynamic regime. Then the idea is that you have to turn the hydrodynamic equations for your fields and observables into effective equations for observables in the full theory which admit a geometric interpretation, because you want effective equations for geometry, for some effective geometry. The other idea is that the only notion of evolution that you can give in such geometric phase and for such observables is relational, meaning it will be in terms of relations between some geometric observable and some internal degree of freedom you use as a clock. So this is a standard way to extract a notion of evolution in cosmology, like quantum cosmology.
So before you mentioned to use the normalization group flow as
No.
as evolution.
Okay, no, maybe I was confused. What I mean is that in order to study whether there are different phases, you have to do the full renormalization group analysis. That comes with some notion of scale or some fine parameter along the trajectory and so on. there's no geometric interpretation as far as we know, no real temporal notion associated with any such notion. So that analysis only is used to establish the existence of a condensate phase. Now we ask a different type of question. Assuming that the relevant phase for the system is a condensate phase, can we extract a notion of geometry, geometric evolution, gravitational physics there? In there, we are saying we need to find observables with a geometric interpretation and degrees of freedom in this geometric phase that we can use as clocks. They may or may not be related at all to what we were using as a scale, abstract scaling, and renormalization group analysis. It's a different step. And relating the two is what I was mentioning earlier, something you probably will have to do in order to extract physical consequences from the phase transition itself.
Right, I was confused because you mentioned also that the Big Bang should be a phase transition, and the relation between the one phase and the other phase is the...
A proper understanding of that statement, of that hypothesis, will require somehow connecting the dynamics on phase space, on the theory space, with the relational dynamics in the geometric phase. But now I'm only focusing on the dynamics in the geometric phase. As I said, all the previous talk about renormalization group, it's only just to motivate why we look in particular for condensate states as the interesting ones for extracting physics.
But then now you are out of the Big Bang regime,
I'm focusing, first of all, I don't know if there is a Big Bang because I don't know if there is GI.
But that question cannot be answered inside the condensate because you are already in the phase of
not directly. Not directly. Okay, and then the extra idea is that you play humble, and as our condensed matter physicists do, you start with the simplest type of states, the simplest approximation, and then you improve. Okay, so this is the Hilbert space we have, Fock space. As I said, the generic quantum states have no geometric interpretation. So the first problem is to identify quantum states in the fundamental Hilbert space with some continuum space-time interpretation. And the general result is that you can give such an interpretation to condensates of the full quantum theory, which can be seen as continuum homogeneous still quantum spaces. Why? Well, take the simplest condensate, which is just an infinite superposition of one body states, two body states, three body states, up to infinite number of quanta, all with the same wave function. It means that if you try to embed all this discrete data into some effective continuum and extract the geometry from the data on the quantum states, you're going to extract the same data from each of the quantum particles or the quanta of your field theory. From the point of view of spin networks, if you come from there, this is a state with an infinite number of degrees of freedom. It just happens to be so special that it's captured by a single wave function, the condensate wave function. Okay, the other point is that, in fact, if you look at this condensate wave function and you look at the domain of the wave function, it is isomorphic to the mini superspace of homogeneous geometries. Why this is the case is basically because if you're really implementing the discrete geometry of simplicial building blocks for each of them, that space is isomorphic to the mini superspace of homogeneous geometries. So, details aside, now you have a wave function that describes a state, collectively a state with an infinite number of degrees of freedom, but is a single function. It is a function on mini superspace. The second problem, once you have this class of states singled out as interesting, is to extract the effective hydrodynamics of the system. And this is, we are very lucky because you just take that class of states that I discussed, you plug it in the fundamental dynamics, say the Schwinger-Dyson equations of your quantum field theory for the endpoint functions. or you use whatever other method you like, you extract a nonlinear equation for the collective wave function. And this is exactly the group field theory analog of the Gross-Pitaevsky hydrodynamics for standard BC, Bose condensates. It's, luckily for me, which I didn't know anything about condensed matter, is the first two chapters of the standard group condensates. Maybe even the first one. Once you look at it, as I said, as a theory for wave functions on mini-superspace, is indeed a nonlinear extension of quantum cosmology for the collective condensate wave function. Now, as I said, formally similar to quantum cosmology, but you are, some of you are philosophers, and you should realize that you're in a totally different conceptual setup. There's no Hilbert space structure behind the effective equation. There is a Hilbert space for the fundamental theory, the Fock space I mentioned, but there's no superposition of states of the universe or no collapse of the cosmological wave function. There's more of a statistical nature for such wave function, because it's the collective wave function, it's the density of the fluid, if you want. So there are a lot of quantum mechanical issues at the interpretational level, as we discussed, for the fundamental theory. At this level, this equation is like an hydrodynamic equation on mini-superspace. Okay, so in this sense, you realized, yeah.
You told us before that it is very important to construct a space-time. How you join the different simplices or the different.
Yeah.
And here the joining was done in a.
No. In this class of states, there's no joining. So you neglected exactly the correlation between the quanta. You gave them the same wave functions. In a sense, they are correlated, but not in.
So I cannot still think that, even though I have this isomorphism, I'm not allowed to think that I have an homogeneous space.
You're allowed to,
Space-time.
you have to say you have a homogeneous space in terms of what sort of observables you reconstruct. You can only reconstruct homogeneous observables. This is sort of a wild close grading. In a sense, the way you should understand it is as the simplest type of approximation of a tentative answers for the ground state, which of course would be full of correlations and entanglement. I mean, a Bose condensate is not, a realistic Bose condensate is not in the Gross-Pitaevsky ground state. The Gross-Pitaevsky ground state is used as the simplest approximation to capture the key features of a condensate phase, and as an approximation to the highly correlated state that would be the actual ground state of the system, even for weak interactions. So, as I said, this is you use your assumptions first in the simplest approximation. You see if everything is compatible with the interpretation, and then you start improving, adding correlations, the gluing, and so on, as the strategy. Okay, let me, how much time do I have?
20 minutes.
How much time do I have?
20 minutes.
20 minutes.
Yeah.
Fantastic.
Well, there's quite, so that includes the discussion time. So
Oh.
we'll want to,
Right.
5 minutes.
Okay, then I'll try to hurry up a little bit, but almost done. So now again, I'll give you the key steps in a concrete realization of this general program that I outlined, with the same general results. What I said is indeed pretty general. In practice, if you want to extract one particular set of equations, you have to pick up one particular model at the fundamental level. So we do that. We pick up, is even a class of concrete models used in spin-foam models and lattice quantum gravity, so-called EPRL models for Lorentzian quantum gravity. Plus, we add an additional variable to the pure geometric simplicial data we had at the beginning. A real variable, which if you look at the Feynman amplitudes of the underlying theory, they give you a discretized path integral for gravity coupled to a scalar field, to a free massless scalar field. So this real variable for each field ends up playing the role of a discretized scalar field at the level of the building blocks. So it's like you added a scalar field, and now you're looking for a continuum approximation of that description. So you have the same type of condensate state with this additional real variable. I'm pretty sure, I'm sure there was something else. So again, there is an interpretation for this data at a discrete gravity level, and now we look for the extraction of an effective continuum description of the same system. We further simplify the condensate wave function to what is basically an isotropic configuration. It's like equilateral tetrahedra with an additional real variable, which is a discretized scalar field. After a bunch of manipulations, you obtain some equation, nonlinear equation for the wave function. The equation has derivatives with respect to the real variable, the scalar field. Some parameters here are functions of the geometric sort of degree of freedom which come from the initial model that we pick up. The same is for the interaction here. And it's a nonlinear equation. There is a quadratic part and a quartic part. Then we assume that the interaction part, although there, is subdominant. So we focus on the previous, on the free theory. Now, having both geometric data and the scalar field type data, you can define in the fundamental theory, as operators acting on the Hilbert space of the fundamental theory, what are basically relational observables. The simplest and key one is the volume coming from the contribution to the total volume from each of the tetrahedra for given value of the real scalar field. So it's a relational notion of volume. It's like the volume at a given value of the scalar field. It's a well-defined observable in the full Hilbert space. You compute the total second quantized expectation value in a condensate state, and you extract, and then you work with this expectation value. This is the V of phi that I write here. Similarly, you can construct other effective observables, but again, as the result of expectation values in the condensate state of microscopic observables.
So these are already expectation values, or these are
this
operators?
This is expectation value in the condensate state, and that's why it depends only on the condensate wave function. Having these observables, you turn the equation for the condensate wave function into an effective equation for the observables. Again, long manipulations, and you get two equations for the volume, the derivative of the volume with respect to the clock, with the relational clock, and for the second derivative of the volume with respect to the clock. So, okay, there are continued equations depending on two conserved quantities, which have no obvious interpretation except that Q is related to the conserved momentum of the scalar field. And then you first of all check, and actually we did it at the end because we were scared, but in a presentation you do it first. You check that for large volume, basically, or small densities, the equations you have here reduce to the classical Friedmann equations for the volume in relational time. And a sufficient conditions for this is that what is just a parameter of the theory, which is basically a function of the microscopic parameters of the theory, is related, basically gives you an effective Newton constant. So if this condition is satisfied, then these equations become the Friedmann equations in relational time. So you're fine with the classical limit. As far as the volume observable is concerned, of course, a lot of other things can go wrong. There's a question coming, yeah?
Yes. So simple question. So the MJs, in principle, could be different.
Mm-hmm. In
Here
fact,
you
they are
assume
different.
that
No, the condition here, in fact, if I want to be more precise, is that there exists at least one J which is dominant in the large volume regime, such that this equality is true. If they're all equal and then it's true for all of them, then okay, it's an even stronger condition, but it's not required by anything. Moreover, you can prove that there always exists at least one J such that the density is different from 0. Which means that the volume, so defined, remains positive at all times and with a single turning point. So what you find is that there is generically what would look like a quantum bounce in the volume observable. So there's no singularity there. Moreover, if you care about the loop quantum cosmology, you can even show that if you take very special condensate states so that they only depend on a single spin, then the effective equation you get is basically the loop quantum cosmology one with some additional state-dependent constant that you can set to 0 with appropriate choice of states. And the fact that a single spin dominates can actually be shown to be true as a result of the dynamics in several cases. So it doesn't need to be necessarily an assumption. Okay, now 5 minutes?
So, I think we should maybe just, if you can wrap up in
I
1 minute or
skip
two.
all the results, all additional results. If you want to know about inflation, I'll tell you. If you want to know about perturbations and other stuff, I can tell you. Let me just close by mentioning singularities. In this scheme, what happens, or what can happen to the cosmological singularity? Well, these are the logical possibilities I can think of before implementing them or not in the scheme. So spacetime has to emerge. If spacetime doesn't emerge, your theory is wrong. So I don't consider that possibility here. The singularity may just not be resolved. It's not that it's a logical necessity that our theory resolves singularities. The singularity may actually turn out to be...
What would be a singularity?
Sorry?
What would
No,
be a
here I'm
singularity?
just listing the in quantum gravity, and then I tell you in our case what the singularity could be, or should be. There may be arguments for which the singularity can be made irrelevant, for example, with the inflation for a long enough time, modulo the Transplanckian issue, but I can imagine scenarios in which somehow there is a mechanism that washes away whatever property you have at the singularity. You may resolve the singularity at the hydrodynamic effective spatial-temporal level thanks to a quantum bounce or some other form of modified gravity theory. Or it could be that the hydrodynamic approximation fails around the would-be singularity, so there's simply no space-time description, not even quantum space-time description around there. And this is, and then if the hydrodynamic approximation fails because you reach some quantum phase transition, quantum gravity phase transition, then it's the sort of emergent universe scenario that Robert was also mentioning. If the phase transition you're approaching is a transition from a non-geometric phase to a geometric phase, then you have the Geometrogenesis that replaces the singularity. So in the context I gave you, in the specific quantum gravity formalism and within I would say, with the GFT condensate cosmology, we found a bounce. So it would seem that we have a bounce in the hydrodynamic approximation. So it's like in loop quantum cosmology, but now in the full theory. So it's great. However, now you have to again be humble and list what are the assumptions you made. So we were in a mean field restriction within an hydrodynamic approximation. So we totally neglected fluctuations. We stayed in the full hydrodynamic approximation, and we assumed that we just stayed in the condensate phase. So, yeah, so there could be a big bounce if the mean field approximation is improved, but there's no breakdown of hydrodynamics overall. In this sense, then, if this happens, then yes, we have a cosmic quantum bounds predicted by our quantum gravity formalism. And that's this. But this is again, if the hydrodynamic approximation holds and if we stay within the condensate phase. The hydrodynamic approximation can break down because you start focusing on very, very small densities. Too few atoms are involved for such values of the density, so you don't trust anymore the hydrodynamic approximation. But also, usually when that happens, fluctuations become too big. In this case, you really have a disappearance of continuum spacetime, because you have a good notion of a continuum geometric observables only in that approximation. And that's the disappearance. If the reason why the hydrodynamic approximation fails is that the quantum fluctuations start driving the system, including all the coupling constants, towards the phase transition, and you reach criticality, then you have the even more radical disappearance I mentioned at the very beginning, and you have a geometrogenesis phase transition, for which, okay. So you're really out of the spatio-temporal phase, and not just beyond space and time. And I think I can close by mentioning that all these scenarios see a precise realization in the formalism, and they can be tested. So there are calculations you can do in the fundamental theory to check which one of them applies or doesn't apply. And this is the list of calculations I can think of, or questions I can think of to address, to know what the fate is of the cosmological singularity. Thank you.
Okay, so we can go into the break a little bit, so we'll get about 10 minutes for questions if that's needed. Please.
Thank you very much. I guess we'll ask one of those philosophical questions. So in case of geometrogenesis, so we have a transition from a non-spatial temporal phase to a spatial temporal phase. So here we are using the vocabulary of phase transitions, of phase, so everything is kind of temporal in a way. So do you think of the situation as, well, we have some kind of second time, the meta time or something, recording whether the underlying system is going through spatial temporal phases and not spatial temporal phases?
Okay.
Is this the kind of idea you have in mind?
So it's, so there are 2 points on the fact of on the question of whether and how an understanding of a phase transition or a definition of phase transition has to be temporal in some sense. Then you can ask your neighbor, and there are notions of having a phase transition, not the other neighbor, of emergence, which are not understood to be temporal processes at all. They need to be understood in that sense, and it is that notion of emergence and phase transitions that can only apply at first at this level. The second question is the more physical one that I was hinting at earlier. If you want them to study for physical consequences of the existence in the mathematics of your theory of a phase transition of that type, then you need, as I mentioned, to relate somehow the temporal evolution, maybe in relational internal variables in the geometric phase, to the evolution on phase space, on the theory space, in the space of possible phases. One idea I have there, but the friend we are doing the project with is now busy with teaching, so we don't have results, is that, so as I said, you can set up randomization group flows for these field theories. That requires that you choose some internal observable, some quantity in the theory that you use as the affine parameter along the RG flow. That's your scale. The idea would be to now redo most of the analysis that have been done for the gravitational models, for models including the scalar field that I mentioned earlier, which is used as a relational clock in the cosmological formulation. and use that clock, that variable, as the parameter along which you compute the G-flow. If you do that, then there is a clear notion in which there is early times, late times in the geometric phase, and you can check if at early times what you're matching is the G-flow as defined by the full RG analysis in terms of the same quantity. But you need to have this matching of the scale and the more abstract RG flow formulation with the clock you use to extract cosmological evolution. That would be the idea.
You mentioned that you mentioned that near the Planck scale, quantum fluctuations could grow and could kick you out from the hydrodynamical phase and have a pre-geometric phase, emergent universe, etc. But you mentioned could. Do you have any?
I mentioned what, sorry?
You mentioned that they could.
Yeah, sure.
Do you have any intuition or preliminary results that indicate one possibility or the other?
So you want to know if it is likely that they do or likely that they don't. So we know, because we've done the calculation, that they're certainly not relevant at the moment the universe expands. Because you can compute volume fluctuations for the same observable we used to describe the homogeneous evolution. And they are suppressed, being extensive quantities, they are suppressed with the total volume. So that's okay. The problem is at low densities, which is exactly what happens in our scheme at the bounds. There, it may depend on the parameters of your model. So it actually is a constraint on the parameters of your model, whether the fluctuations become too big or too small, or they are still...
And you are thinking about fluctuations in the volume. So it's still
that's the first one. So far I only discussed the evolution of the volume.
Homogeneous sector, not
The
fluctuations.
No. We're
Deviations
talking
from
really about the
homogeneous.
quantum fluctuations for the same observable we used to describe the global evolution. Of course, the second step is a different type. I studied a particular class of solutions to the full quantum dynamics, the ones that have an interpretation as homogeneous universes. You can take fluctuations in the fundamental dynamics around them and check if the system is stable under those fluctuations. That's also a calculation you can do. I mean, there's no obstacle in principle. There is an obstacle in time and computational abilities. But with smart collaborators, you can do a lot.
Josh is
Thank you, Daniele. We talked about up here, we have a special condensate state that then gets mapped into some continuous geometry. But not all states are condensate states. Can you tell me a little bit more about what makes these states special? Or what do we need in order for it to be a condensate state?
Okay, what makes these states special? Okay, so I try to motivate why we first focus on condensate states, because we look for non-trivial phases of the theory, and the RG flow studies that we've done so far seems to suggest that the first type of non-trivial phases we are going to encounter are the condensate type. That's one reason. The other reason is also what I mentioned, that this idea of condensation of different quanta being at least approximately with the same wave function is a sort of a quantum part of homogeneity. So in this sense, they have a rather straightforward interpretation in terms of homogeneous geometries. The third reason that I probably shouldn't state so openly in public is that they are so simple. That condensate state is really so simple that assuming that's a good approximation to the ground state, that the hydrodynamics can be literally extracted in 10 lines of calculation from the fundamental quantum dynamics. In general, the problem of extracting the hydrodynamic effective equation from some generic state is incredibly hard. Unless, of course, you know all the symmetries of your theory and so on, which we don't fully control for this class of fluid theories. Otherwise, you wouldn't look at the microscopic derivation, you just list your symmetries and write down the most general thing that is compatible with that. But it requires a lot of understanding of a different type.
will be the last question, I think.
Okay. It has two parts. One of it is, I would like to know if you agree with the following statement.
Yes.
The fact that you have, constructed this condensate or this description of, many copies of things on the same state should not be yet considered as equivalent of recovering an homogeneous space-time in the following sense. The relation between the different elements of even of a space, even though they are identical, the pieces are identical, the relationship between one and the neighboring one is very different than the relationship between that one and a farther away. And one that is farther away. In other words, you should be able to extract some notion of two elements that are very distant and 2 points that are very close, even though they are all here appearing in the same footing. And the second question, this one is a yes or no, but the second one is a more, it's intended to be a more bothersome one. These correlations, these quantum correlations that we need to have in order to recover something that could be considered as, let's say, an homogeneous space-time, are probably very complex correlations, because, for instance, if I look at the field part, just a simple scalar field part, I know that, for instance, in the vacuum state, which is homogeneous, the correlations, the quantum correlations, depend very, very particularly on the separation. Otherwise, your state is not a Hadamard state. You don't have a Hadamard type correlation between the two-point functions. And therefore, establishing that kind of complex correlation is something that would have to be, required in order to say, yes, I have obtained something sensible.
Okay, so I told you I agreed, right? So I agree with the general point. Let me clarify how I see this task in my language or in this context. So there are 2 points. So your argument has to do with the physical characterization of homogeneous geometries. And the statement about the universe being homogeneous is really a statement about inhomogeneities doing something. Being possible to neglect them in some way, or being correlated in such a way that, you need to know what your inhomogeneous sector really is physically to say that you have gravity, first of all, and second, that in a certain approximation everything looks just homogeneous. So from this point of view, it requires much more than just extracting an effective Friedman dynamics. You need to extract a good physics of inhomogeneities and then show that there is an appropriate sector of that, or approximation of that, or cos-graining of that at the continuum level that gives you the homogeneous description. In fact, the same is true at the fundamental quantum level, in the sense that, as I emphasized earlier, there's no pretense that the ground state of the system of an interacting quantum field theory, although more abstract and so on, is so simple, and in particular such that you can basically neglect all the correlations and the entanglement and so on. This is clearly false. At best, is an approximation to something else. So at the level of the quantum description, before you look for the geometric interpretation, you should also show that the type of state for which you had an approximate interpretation as a homogeneous geometry is a reasonable approximation of a more realistic ground state of the theory. And again, this means that you first have to control the quantum correlations of the fundamental theory and then show that in a certain regime, the one that you used earlier, they can indeed be neglected. And so they are both very complex tasks. And yeah, of course, I'm aware of that.
And they're open.
I can tell you some partial results on each of this, but yes, of course they're open. Otherwise, I would tell you the full story, right? Of the stupid approximation.
Thank you.
So we're out of time, so we join me in thanking Daniele again.